So now we're starting a new chapter. In the previous chapter, we looked at some basic methods that we could use to find the derivative of a function. And now in chapter 3, we are going to look at how we can apply the derivative to analyze the graph of a function. So a lot of the behaviors that we will be looking at, they're listed here. We can look to see where the graph is increasing, decreasing, or constant. We can see whether it's opening upward or downward. So we would use the words concave up and concave down for that. Another feature of the graph that we can look for is the highest value or the lowest value relative to the points nearby, and that's called a local max or a local min, because in that area, it's a maximum or a minimum. So it's only local maximum or minimum. It's in the neighborhood. So for number 4, another feature of a function that we can look for is the absolute highest and absolute lowest value on that graph, either for the whole function or on a specific interval. Now that is called the absolute max and the absolute min. We can look for asymptotes, and then we can also find where the function crosses the x or y axis. Well, the main focus of this section is we're going to talk about how we can use the first derivative to find some of these features of the graph. In this lesson, we're going to focus on what information we can gather from the first derivative. So if you look here, it says suppose that the function is continuous and differentiable, defined on an interval. So remember back in chapter 1, one of the topics that we discussed that we put a big emphasis on is the continuity of a function. And we said that that was important because a lot of our theorems or tests depend on the function being continuous. So here's one of those examples. In order to have these following 3 items, the function needs to be continuous and it needs to be differentiable on this interval, a to b. Notice that this is an open interval. So open meaning that if I was looking at the interval, it wouldn't include the endpoints. This first statement says, if we look at the derivative of the function and it's positive, it's greater than 0, then for every value of x on that interval that we're looking at, the function is going to be increasing on that interval. Conversely, if f of x is increasing on that interval, then the derivative has to be positive on every one of those values of x on that interval. So the first statement is basically saying when the first derivative is positive, the function will be increasing on that interval, and then it works in the reverse direction. If we look at the function first, on the intervals that it's increasing, the derivative will be positive. For statement number 2, we have if the derivative is negative, if it's less than 0, then for every value of x on that interval, the function is decreasing on that interval. And then it works in reverse as well. If you look at the function first and you see where it's decreasing, then you know that on that interval, the derivative would be negative. Statement number 3 says, if the derivative is equal to 0 for every value of x on that interval, then the function is neither increasing nor decreasing on that interval, but it's a constant on that interval. And then again, it works in the reverse direction. If you're looking at the function first and you see that it's a constant function on the interval a to b, then we know that the derivative on that interval is going to be 0. So we are going to use in this lesson, and this is going to be our biggest focus, is the first derivative test. And this is going to help us determine, using the derivative, where the function is increasing or decreasing. So we're going to call C a critical value. Now, a critical value is when you find the derivative and you look for values of x that make the derivative either 0 or undefined. those values of x that make the derivative 0 or undefined are considered critical values. So the first statement for the first derivative test says f of x is increasing immediately to the left of c and decreasing immediately to the right of c, then c produces a relative maximum. So what this is saying is if you have a value of x, that when you take the derivative and plug in that value of x and you get 0, that's considered a critical point. And on one side of that critical point, it's going to be increasing. On the other side of that critical point is going to be decreasing. So you have a function that's increasing, and then it comes to a point at the top, and then it starts to decrease again. When that happens, it's considered a local maximum. And then the same idea goes for number 2, but that would be where we look at that critical value, and if we look to the left of it, it would be decreasing, and then when we look to the right of it, if it's increasing, that would produce a local minimum or a relative minimum. So looking at this point right here, the relative maximum, if I look directly to the left, this would be an increasing interval here, and this would be decreasing here. So that's what makes this a relative maximum. Looking here at our relative minimum, I have it decreasing on the left and increasing on the right, and that's what makes this a relative minimum. Looking at our first example, we have the function x to the third minus 3x squared minus 9x minus 1. And I have that function graphed here. I use GeoGebra to graph it. So you can see that it's a cubic. We can see that there are intervals of increase and decrease, and we can see that there's a local max and a local min. Now we're going to use the first derivative test to find these specific intervals and points. So if we're going to use the first derivative test, we have to find the first derivative. So when I take the derivative of x to the third minus 3x squared minus 9x minus 1, I get 3x squared minus 6x minus 9. Now I wanted to clean this up a little bit because I know that I'm going to end up setting this equal to 0. So what I did was I factored out a 3, and then I factored what was left over, the x squared minus 2x minus 3. So this is our derivative in factored form. So when we go to find our critical points are the values of x when the derivative is equal to 0 or when the derivative is undefined. So because this is a polynomial, we don't have any places that we would have an asymptote or a hole in the graph where it would be undefined. So I'm really going to focus on setting the derivative equal to 0 for this one. When I set this to 0, I get that my values of x are 3 and negative 1. So when we get our critical values, we set up what's called a sign chart, and the sign chart is going to help us find those intervals of increase and decrease in the local maxes and mins. What you want to do is you want to place those critical values on a number line and make sure that those numbers are listed appropriately on that number line. I want to make sure that reading it left to right, that's going to be increasing values. So by putting these two values on here, I have negative 1 and 3. This is my preference. Everybody does it a little bit differently, but my preference is where the first derivative is 0, I just put a little 0 above those values. So at negative 1, the first derivative is 0. At x equals 3, the first derivative is 0. Then what you're going to do is you're going to pick test points. So by putting the negative 1 and the 3 on this number line, I split the number line into 3 intervals. I have this interval here from minus infinity up to negative 1. I have from negative 1 to 3, and then I have from 3 to infinity. I want to pick a test point on each of those intervals. It doesn't matter what the test point is as long as it lies on that interval. And you cannot use your critical values. It has to be something in between. For this interval here, I chose a test point of -2. So what we're going to do is we're going to plug -2 into our derivative. So when you plug -2 into the derivative, I get a positive 15. So on your sign chart, you are going to list, however you want to list it, you're going to put positive signs or something to indicate that this is a positive interval. Because this is a positive interval, the function is going to be increasing on this interval. So from the interval from -infinity up to -1, this is going to be increasing. And we can verify that on our function. -infinity, so we're scanning the graph left to right because we're looking at our x's. We're not looking up and down. This isn't y is -infinity. This is x is -infinity. So as I go left to right, when I get to -1, that's where I pause. Think about it as a roller coaster. So I climb the roller coaster and then for a moment I pause at the top and then I start coming down. When you have that pause, that's where your derivative is equal to 0 because that's where your tangent line has a slope of 0. So this interval here is increasing. Then we pick a test point between -1 and 3. I personally like to use 0 whenever I can because it makes the arithmetic easier. So on this interval, I chose my test point to be 0. When I plugged in x is 0 into my derivative, I got the answer was -9, which means it's going to be decreasing on this interval between -1 and 3. And if you look at the graph of the function, between your pauses on your roller coaster, I have a pause here and I have a pause here. That's where it starts to decrease. So that's between -1 and 3. For the last interval from 3 to infinity, I picked x is equal to 4 to plug into the derivative. When I plug in x is 4 into the derivative, I get a positive 15. So on this interval here, it's going to be positive, which means the function is going to be increasing. So from 3 to infinity, here's x is 3 to infinity. This is x is infinity, not y. So we're looking at horizontally, we're going on forever in the horizontal positive direction. So from 3 to positive infinity, we're going to be on an increasing interval. Now, when you compare the graph of the function and the graph of the derivative, it's an extra resource or visual aid to see what's going on here. Here's our original cubic, our graph of f of x, and I indicated and color-coded intervals of increase in this pinkish purple color and intervals of decrease in the green. If you notice, where the graph is increasing on the function, not the derivative, if we look on the original function where it's increasing, that would mean that the derivative would have to be positive on that interval. And if you look at the derivative, positive means it's going to lie above the x-axis. So anywhere that it's above the x-axis is going to be where it's increasing on the original function. So -infinity to -1 on the derivative should be positive, meaning above the x-axis. Then when we look at the interval from -1 to 3, that's this interval here where it's decreasing, that is where on the derivative it falls below the x-axis because that is where the derivative is negative, which means it's decreasing on the function. And then the same thing goes for this pink area here. When I look at 3 to positive infinity, that's increasing. So on the derivative, those values on that interval should be above the x-axis. That's here. Now, the places where the derivative is 0, that would be here and here. That on the function is going to be where our we have our local maxes and mins on this function. So this is our local max, and this is our local min. So that would be where the slope of the tangent line is 0, which means the derivative is going to be 0. And if the derivative is 0, that means it's where it crosses the x-axis. So these points here indicate a local max or a local min. So looking at the sign chart, we labeled where it was positive and negative. Now let's use the first derivative test and talk about how we decided where it was a local max and min if we were not looking at the graph. We can see it on the graph, but we want to do it with just the sign chart. So again, I color coded this, pink where it's increasing, green where it's decreasing. Because this interval has positives, that means the function is increasing. So I drew an arrow going up. This is just my preference. You can do it however you want. And then to the right of that critical value, on this interval here, it's negative, so it's decreasing. And the first derivative test says if you're looking at the critical value and it's positive on the left and negative on the right, then that's going to indicate a local max, right? I come up and then I come back down again. So that point where the derivative is 0 has to be a local max. This point right here, for this critical point, right to the left, it's negative. To the right, it's positive. So it's going to come down, hit that lower point, and then go up. So this has to be a local min based on the first derivative test. This was a nice, easy one to get started. I have a more challenging one next. I wanted to make sure that I picked an example where when we found the derivative, there were critical values that made the derivative undefined, so we can see what happens there. So here's our original function, and I have it graphed over here. So we have this, it's increasing here, then it comes down, and we clearly have an asymptote right here. And then it comes down, it looks like a little reverse cubic here. And then we have this piece right here. So we have two asymptotes here, or at least two vertical asymptotes. We also have a slant asymptote right here as well. So here's our original function. Using the quotient rule, I found the derivative. So I want to take the derivative of the top, which would give me 6x squared, times the bottom. So that's the x minus 2, x plus 1. Then I wanted to subtract the derivative of the bottom times the top. Now, because the bottom is a product, we have to use the product rule here when we take the derivative of the bottom. So that is this right here. I put it in braces so that you can see the difference between the brackets and the braces and the parentheses. This, using the product rule, here's my derivative. I take the derivative of the first, which is just 1, times the second. And then I add that to the derivative of the second, which is the x plus 1, which would be 1, times the x minus 2. And then, so this is the derivative of the bottom using the product rule, and then I still have to multiply that by the top because of the quotient rule. So this one's got a lot of stuff going on in it. And then I take the bottom and I square it, and that will give me my first derivative. So then I took some time to expand it and simplify it. I didn't expand the bottom because I know that I'm going to need that to be factored. So when you're looking for values that make the derivative negative or undefined, you're going to want this factored so that you can find those values of x that make the denominator 0. So the critical values are what makes the derivative 0 or undefined. Looking at this first, the places where the derivative is undefined is where the values of x make that denominator 0. So that's going to be 2 and negative 1. So now let's look at what makes the derivative 0. Now, because we have a fraction here, all I care about is when the top is 0. As long as the bottom isn't 0 at the same time, we only care about making the top 0. So I can completely ignore the bottom because 0 over 5 is 0. 0 over 100 is 0. 0 over negative 1,000 is 0. If 0 is on the top, the whole fraction is 0. So I just focused on the top and I set that equal to 0. And then I factored out a 2x squared, which left me with x squared minus 2x minus 6. This does not factor nicely, so I went ahead and used the quadratic formula to find these values here. So solving the quadratic formula, I got 1 minus the square root of 7, and I got 1 plus the square root of 7, and these are the decimal approximations for those. When I look at this factor here and set that equal to 0, that's going to give me an x is 0. So x is equal to 0, and these two values here is what I would plug into the first derivative and get out 0. So I have 1, 2, 3, 4, 5 critical values here. So this is going to be a fairly lengthy sign chart. So on the sign chart, I labeled my numbers appropriately. I don't necessarily care if it's scaled in this case. Like you have to go make, tick marks by 1 or whatever. I just want to make sure that the numbers are in order because all we're really looking for is what happens in between. So scaling it, you can if you want, but it's not necessary. So here's how I broke up my sign chart. I went from the smallest critical value to the biggest critical value. And then above each one, I labeled what that was. So at negative 1.65, that gave me the derivative is 0. At negative 1, that gave me that the derivative is undefined. This is important to label it. It doesn't matter how you label it, but make sure somehow you label it so you know what these values represent. That's going to help you determine where your local maxes and mins are. So then I picked test points. So these are the test points that I picked. I picked -2 for this interval. Then I picked -1.5 for in here. And I'll let you read the rest. I won't read it all out. But here were the values I picked for my test intervals. And then I plugged them into the derivative, and these were the values that I got. So on the first interval here, where I picked the test point of -2, I got a +1. So this is going to be increasing here. So I made a pink arrow. These from -1.5 all the way up to 2.5, up to this test value, these were all negative. So I made all of these green arrows going down. The last test value on this last interval here was positive, so I made that increasing. Now let's verify this with the graph. If I trace this left to right from minus infinity, that's this interval right here, up to -1.65, it's increasing. Then at that point, we hit the top of the roller coaster, we take a pause for a second, that's where the derivative is equal to 0, and we have that labeled right here, and then it decreases. That's this interval right here. Then, because there's an asymptote here, we have to pick up our pencil. This is a discontinuity. And then we start back up here and follow that left to right. That's going to be decreasing the entire way from here to here, the whole way. This is where we have our asymptote at -1. This is where we have a critical value that's 0. So it flattens out here. So we have a tangent line that has a slope of 0 at that point. And then we have our second asymptote that's right here at x equal to -2. And from 2 to 3.65, when I pick up my pencil at the bottom here to continue left to right, this is still decreasing. And then when I hit the bottom of our local min, I start to increase again. Now, I only have 2 local maxes and mins. That's this one here and this one here. The first derivative test says if you're looking at a critical value, and you have a critical value that's 0, so your tangent line has a slope of 0, then if you're increasing on the left and decreasing on the right, that is going to be a local max. So that's what this is. It's increasing on this side, then it hits that point, and then it decreases on this side. So the point at x equals negative 1.65 is a maximum, or a local maximum. This point right here, x0, this is a critical value, but if this was a local max or a local min, on opposite sides of that 0, one would have to be increasing and one would have to be decreasing. This just tells me here, because the arrows, because on both intervals it's decreasing, that I just know that it flattens out at 0, and that's what gives it that horizontal tangent line. So as I follow this and I hit x is equal to 0, it just flattens out and then it keeps going. Now looking at this point here at 3.65, I know by looking at the graph that that's a local minimum, and I know by looking at my sign chart that that's a local minimum, because on the left side it's decreasing and on the right side it's increasing. So down here I listed the intervals of increase and decrease and the local max and local min. Now when you put your intervals for your increase and decreasing in your homework on XYZ, you have to put that union symbol in there, and that will show up in your symbol palette. Now let's look at the function versus the derivative. So here's our original function. I highlighted the areas of pink where it was increasing. The areas that are decreasing are highlighted in green, and then I put a dot at our local max and min. Because our derivative is equal to 0 at these dots where we have a max and min, then that's where it's going to cross the x-axis. Actually, I forgot my little dot here. The slope of the tangent line at that point is 0, but it's not a local max or min. But it should still come up here as a 0 because the slope is 0. So on the graph of the derivative, we would have that point where it crosses or touches the x-axis. So anywhere on the function that's highlighted in pink that's increasing, on those intervals on the derivative, it should be above the x-axis because it should be positive for the derivative. So on those intervals, right here and right here, it's above the x-axis. The intervals in green where it's decreasing, on the derivative should fall below the x-axis so that you get a negative value for the derivative, which is why the function is decreasing on those intervals. Okay, last topic, we're going to talk about what is called the absolute maxima and absolute minima. This is just a fancy way of saying the absolute max and the absolute min. The absolute max and the absolute min is going to be when you look at the entire graph, or if you're looking at it on a specific interval, you want to find the values that are the highest and the lowest. Sometimes that overlaps with the local max or min, and sometimes it doesn't. So looking at this example here, when we're looking at this function from the interval a to b, we have two local maxes here and here, and those are called local maxes because in that area it's the highest point. It's in that neighborhood. And then we have a local min right here because in this neighborhood that's the lowest point. But if I look at the entire interval, what is the absolute lowest point? That would be this value right here, which is why this is labeled absolute minimum. For the absolute max, that would be this. So in this case, this is a relative max and an absolute max. It's the top of a hill, so in that neighborhood, it's the highest point. But when you look at this interval, this is the absolute highest point. So this is also considered the maximum, the absolute maximum. Here's another example. When I look at this interval of this function, this point right here is the local max and it's the absolute max. It's the local max because it's the top of a hill, and it's the absolute max because it's the highest point of that function on this interval. Now, to find a local min, that would be right here, although it's not labeled on here, but we would have a local min here. Now, believe it or not, because this is open here, it's not closed like it was over here. Because this is open, there is no absolute minimum. And that is because this is open. So let's say this point, if we make the assumption, just to get some values here and think about it, let's say this value of f right here is 1. So if this was 1 on the y-axis, you can't say that the absolute min is at that point because there's no value there. There's a hole, it's open. So what's to stop us from saying, well, why not 1.1? Is that the absolute min? Absolutely not, because this is an open circle. I can get even closer. Well, what about 1.01? That's even lower, closer to that point. So now we're thinking about limits. How close can I get to that point? We're going to get points closer and closer and closer, but we're never going to reach it. No matter what point you give me, I can give you one lower, which means there is no absolute minimum on that graph. On this graph, this would be our absolute minimum. There, because this is an open circle, for the same argument, we do not have an absolute maximum on this graph. If this was at the point 1, for the same reason, if this was 1 here on the y-axis, we can't say that the absolute maximum is 1 because there's a hole there. But someone can say, well, what about 0.99? But I can find a point closer than that. It would be 0.999. So that would be higher than the 0.99. And I can always find a point higher than that keeps getting closer and closer to that open circle. So there is no absolute maximum on that interval. Looking at this interval, we have this is a local max, this is a local min. In this case, we don't have absolute max or absolute min because we have both open circles here. And again, for that same argument, we can always find a point higher or lower, which would not allow us to ever find a maximum, an absolute maximum, or an absolute minimum. This one's a little tricky because after finishing this one, when we look at those open circles on the endpoints, we want to say that there is no absolute max or absolute min. And we have a similar situation here. So when we look at those endpoints, it might catch our eye and say, oh, there's no absolute max or min. But in fact, there is. Because of the shape of the graph, we have a local max here that is the absolute max. And then we have a local min here that is the absolute min because that's the lowest point on the graph, and this is the highest point on the graph. Open circles on the endpoints do not indicate that there is not a local max or min. You have to be careful and look at the whole entire picture and don't just get caught up on the endpoints.